Um, Good afternoon. This meeting will be recorded and posted to YouTube tomorrow. So welcome to the Particle Astrophysics installment of the Big Questions in Particle Physics, a colloquium series sponsored by Snowmass Early Career Core Initiatives. My name is Tiffany Lewis, and I'll be today's moderator. I'd like to recognize also Christy Engel, Josh Barrow, and Jorge Torres for their work on this series. So Snowmass is a community planning process whereby the scientific community self-organizes and reports the most interesting questions of the day to DOE, NSF Physics, and NASA. Astroparticle physics is primarily covered in the cosmic frontier of the Snowmass process, and the cosmic frontier is in the midst of their organizational meeting for the topical group reports. The second half of that will be held on April 5th at 3 p.m. Eastern, with astroparticle physics addressed in the first half hour. So today we are going to be hearing from two different speakers who will share about the future of particle physics. Each speaker will have 25 minutes of individual time, followed by 5 minutes for individual questions. After John and Jordan have both spoken and answered individual questions, there's about 20 minutes reserved for a broader discussion of the future of particle astrophysics and the role of Snowmass in it. Questions may be entered in the provided Google form anonymously, and additional questions may, you can raise your hand during any of the Q&A sessions. So our first speaker today, stop sharing, is going to be John Beacom. He's the Henry L. Cox Professor of Physics and Astronomy at The Ohio State University and Director of CCAP. He received his PhD from the University of Wisconsin in 1997 and has been named a Fellow of the American Physical Society as well as a Fermilab Distinguished Scholar. His main research interests lie at the intersection of the fields of astrophysics, particle physics, and nuclear physics. John also co-chaired the panel on particle physics and gravitation for the Astro 2020 Decadal Survey. And I'll turn it over to John.
Okay, good afternoon. Is that all good on audio and video?
Yep.
Okay, thank you. Welcome, everybody. Particle astrophysics is about making connections. Making connections includes the vast, majestic complexity of the observed universe to the powerful simplicity of the microscopic world. In other words, we seek to understand the mechanisms behind the majesty of the universe. Hang on a minute, there we go. Okay, so you all are particle physicists, and what are the goals of particle physics? Most obviously, to probe fundamental particles and forces, to figure out how that translates into emergent phenomena. For example, you might be starting with the QCD Lagrangian on the first line, and you might be trying to understand nucleons and baryons and everything else on the second line. And of course, it's to search for new physics, for laws that we haven't met yet. So what's the particle astrophysics part of this? Well, we'll get there. There's three ways to advance progress in particle physics. And the most familiar one is in the laboratory. And of course, you're familiar with also the importance of using cosmology and astronomy. So in the laboratory, we make measurements of particles one by one. We can keep track of them and we know exactly what's happening in controlled experiments. In cosmology, we don't measure particles one by one. We measure just the bulk properties of a group of particles in a volume, basically a density. And in astronomy, we take what nature gives us. So whatever falls from the sky, that's what we try to make sense of. And the laboratory studies are, of course, the highest precision and they're wonderfully controlled experiments. But cosmology has also, we're deep in the area of precision cosmology now, and it has great advantages, including being able to probe basically small effects compounded by giant distance scales and huge volumes. And using astronomy, we have also the opportunity to probe conditions that we just can't reach in laboratories on Earth. Extremes of high temperature, high energy, high density, distance. And this is what this talk focuses on, is the particle astrophysics part. And when I started in grad school, it was before cosmology was called precision cosmology. And I think we're now entering an era when astrophysics is starting to become precision astrophysics. And I think not everybody in particle physics has fully appreciated that point, but it's super important for the direction of the field in the next decades. So what exactly is particle astrophysics and what do we do? Particle astrophysics, we want to make two trades. The first trade is we want to get new knowledge of particle physics by ideally simultaneously improving our knowledge of astrophysics, or at least using our knowledge of astrophysics. The other thing we want to do is we want to gain new knowledge of astrophysics, again, ideally at the same time as particle physics, but at least exploiting our knowledge of particle physics. And the trick about this is we have to do both of these things at the same time. There's a reason that laboratory studies are the predominant mechanism of progress in particle physics. It's because we can control the beam, we can control the target, we can control the detector, we can control everything and figure out, isolate one new thing at a time. In astrophysics, where whatever we observe just falls from the sky without our preparation, it's much more challenging to pick things apart and to figure out how to advance the particle physics and the astrophysics at every step in a way that is not circular. So in order to do this, we're going to use a variety of probes, and this is why it's called multi-messenger astrophysics, and we have to choose our fighter. And actually, my choice is all of them. So the one that's most familiar to astronomers is the one in blue, the ordinary sub-MeV photons that are used in astronomy departments, radio waves to X-rays. And these are the best probes of not only thermal sources, but some non-thermal sources. And the photons can be detected in great abundance. They can be detected with very high efficiency, with incredible angular resolution, all of that. Everything you know about astronomy is the first line. And what we're trying to do is start to develop these other 5 messengers to develop their power. They'll never be as powerful as ordinary electromagnetic astronomy, but they can be very powerful. And they can be very powerful because of basically the long lever arm that they have. And I'll go back to that in more detail. But basically, each one of these has some special powers. For example, cosmic rays are direct probes of cosmic accelerators. And we know that nature can make fantastically better accelerators than anything we have on Earth. I mean, reaching much higher energies and incredibly higher luminosities. And we don't know how nature does that. The problem with the cosmic rays is, of course, that they deflect in magnetic fields. And if we keep going through these one by one, I think this is all familiar to everybody. All of these multi-messengers have some advantages and some disadvantages. But by collecting all of this data and comparing them to each other, we have a chance to figure out the truth. So of the 4 green messengers, we have now detected gravitational waves only recently, and high energy astrophysical neutrinos also only recently. Dark matter has yet to be detected, but once it is detected, it will become another one of our messengers. So not only do we have to choose our fighter, we have to choose our arena, and these are also plentiful and incredibly different physical conditions in them. So ranging from the stars and planets and supernovae to galactic scales with, how a galaxy forms, why the halo and the subhalos shaped by dark matter formation and a dark matter structure formation, to the bubbles above the disk seen in gamma rays and other wavelengths, to the cosmic scales, including how galaxies are shaped, and of course, the CMB and BBN and everything else like that. There's really a rich panoply of places we can be looking for particle astrophysics signals. So here's what I want to cover today. There's so many things in particle astrophysics. Jordan and I have tried to come up with complementary talks. I'm focusing a little bit more on theory and some of the big questions, and Jordan is focusing more on experiment and some of the how we carry all of this out. And in this one, I'm also going to focus on high energy multi-messenger astronomy. I'm, for example, going to leave out dark matter, even though it's a huge and important topic. I'm going to leave out supernova neutrinos, solar neutrinos, lots of huge important topics. We just can't cover everything today. But I think the story that I chose is, I think, a nice one because it's about cosmic rays, gamma rays, and neutrinos and how they all talk to each other. So here's what we'll cover today. 3 frontiers of looking at cosmic rays, gamma rays, and neutrinos. These are different from DOE's frontiers. And I call this the extreme coverage, which means the place where we have the incredible precision data and an incredible breadth of data. Luminosity is where the highest luminosities, and extreme energy is, of course, the highest energies. So as an example of the extreme coverage frontier, I'm going to talk about our own sun, as which has been seen blazing in gamma rays from all throughout the GeV range. The sun is actually one of the brightest gamma ray sources on the sky. You don't normally see it in Fermi maps because it moves. But if you adjust your coordinates so that it doesn't move, it appears as an extremely bright source. And the most fundamental thing I want to tell you is about this, the sun is an incredibly bright source of gamma rays and nobody knows why. And if we can't understand our own sun with the best, basically the best data we will ever have on any star, then that's a stumbling block towards understanding more complex things in the universe. So we have to get this right. So we do know that these gamma rays are produced by cosmic rays interacting with the sun's magnetic environment. But how they do that, nobody really knows. And we do know that it's hadronic collisions that make gamma rays and neutrinos, but the details are unknown. And we might wonder what other processes can do this, and we actually have some ideas. One thing we know it is not, it has nothing to do with solar flares. The sun is blazing because it's being irradiated by cosmic rays. Other possibility is there could be some dark matter annihilation processes that take place. We'll come back to that. Okay, so what does the sun look like? This was first observed by Fermi about more than 10 years ago. And in this picture on the left, you can see a little bright spot in the center. That's the disk of the sun. And around it, you can see sort of a glow, and that's what we call the halo of the sun. The figure on the right is a control sample where we look away from the sun's direction. So it's rather boring. And this disk emission, if you look at it as a function of angle from the sun's center, the disk emission is very bright, concentrated. And then there's this more diffuse emission throughout the halo that goes out to very large angles. Not shown in this figure, but Fermi measured it out to about 10, 20 degrees. Now, the short version of this is all of the emission from the disk is caused by cosmic ray hadrons that hit the disk and somehow produce gamma rays. The somehow is an important word, but the disk is cosmic ray hadrons hit the disk and interact with matter. The halo is cosmic ray electrons hit solar photons, undergo inverse Compton scattering, and make high energy gamma rays. I'm not going to talk more about the inverse Compton component, the halo. I want to focus on the disk because the disk is the part that is the most confusing. This figure on the right shows some earlier predictions from Seckl, Stanev, and Geiser. And then you can see the Fermi data right there in the middle. Now, this figure is missing a couple of things. First of all, this stuff at the top that says naive model, that is not actually a model. You should just ignore that. The interesting part is their main prediction down here in the blue is below the data. And the most naive prediction of the emission from the sun is actually much, much, much lower. And what Seckl, Stanev, and Geiser did was they figured out a way to enhance the gamma ray emission from the sun. So the original prediction would have been like way down here. Seckl, Stanev, and Geiser predicted up here, and the actual emission is even higher. So what did they do? If you don't have magnetic fields, then cosmic rays that come into the sun will make pions and gamma rays, but all of that will be absorbed by the sun and it won't get out. Seckl, Stanev, and Geiser said, how about if a proton comes screaming in towards the sun, dips under the surface, turns around in the magnetic fields, and then interacts on the way out, making pions and gamma rays on the way out. That means that the sun has to very efficiently turn around protons just as they dip under the surface of the photosphere. And that is these blue lines. And the data is actually higher. So we don't know the exact mechanism of how those magnetic fields work, but it has to be happening in some way. So we've pursued that further and done our own analyses with Fermi data led by Tim Linden. And here's what Fermi did in 2011, the black points, and here's how we've extended it with the red points during solar minimum. And it is basically a pure power law over about 3 orders of magnitude, which is mysterious. It has the dip near 40 GeV, which is extremely mysterious. And it maybe has an endpoint somewhere, and that's all interesting. So we don't understand why the flux is so high. We don't understand why the spectrum is so hard, because the cosmic ray spectrum is falling like e to the minus 2.7. The gamma ray spectrum is much harder than that. It's more like e to the minus 2.2. And we also don't understand the time variation that during solar minimum, the gamma ray emission is much brighter. During solar maximum, it's much dimmer. So there's a lot going on here. And there's a lot of opportunities to go further. And one of the things we've been doing is working with the Hawk collaboration, and Maren Nisa, I believe, might be here. She has led one analysis with Hawk data and is leading another now. And the attractive thing about the Fermi data is it's zooming along, zooming along, zooming along. And at some point, it's going to stop. And then here's the upper limits from Hawk. So that tells us that there must be a transition somewhere in there. And measuring the energy of the transition will be an important step to understanding what the heck is going on. So that will be forthcoming soon. And when it happens, you should have a talk from there. This is in a broader picture of understanding the sun in a multi-messenger approach. Many pictures on the left. On the right, we show where the gamma rays come from on the surface of the disk. If you look in the bottom left panel, during solar minimum, the gamma rays come more from the equator. You can see that most easily if you look at the projection here on the side. And during solar maximum, the gamma rays come mostly from the poles. And you can see that most easily again if you look at the projection on the side. How this works, we don't know. So ultimately, we're going to use this to try to understand how cosmic rays interact with the sun. And once we do that, we can use that to understand searches for new physics with the sun. One potentially crazy idea is that dark matter annihilates, collects in the solar core and annihilates. And normally it would just, its particles would be released in the solar core and that's the end of them. But if there's some long-lived mediators, then those might decay outside of the sun, giving visible gamma rays and less attenuated neutrinos. And again, with Mayer and others, and the Hawk collaboration, we've set a bunch of limits based on those processes. Here's Mayer's upper limits, and we think we can go much further. So to conclude on the sun, even basically one of the most boring stars in the universe, we don't understand it. And there's a lot that we can learn both about the astrophysics and the physics. So turning now to what I call the extreme luminosity frontier, this is basically the ordinary cosmic rays in the Milky Way. So these are nature's most luminous accelerators. They're powering almost all of the cosmic rays, which affect how galaxies work. We have not seen evidence of dark matter annihilation or decay, but we keep looking. And ultimately, we should be able to see these neutrino signals and look for tests of neutrino properties. There are basically 2 ways to make gamma rays. I'll start with the second one first, the leptonic mechanism. Cosmic ray electrons can inverse Compton scatter photons and produce high energy gamma rays. And when that happens, you just make it gamma rays. However, you can also produce gamma rays through the so-called hadronic mechanism. And when that happens, not only do you produce neutral pions that make gamma rays, you also produce charged pions that make neutrinos. So in a hadronic accelerator, gamma rays are always accompanied by neutrinos. And in a leptonic accelerator, they're not. So when you just see gamma rays from a source, you can't tell which of these 2 types of accelerator it is. But we do know that all accelerators make a mess. And the reason they make a mess is because just the high densities of matter and radiation around the accelerators inevitably provides targets. And then when the cosmic rays propagate to us, they make even more of a mess, meaning more gamma rays and neutrinos. So what have we observed? This is a lower energy range than what I'm focusing on now. This is the GV to TV range seen by Fermi. Fermi has seen our own Milky Way plane very beautifully. This is a diffuse emission. We're living in the plane, and so we see it as a line. And then this is the halo of the Milky Way and the halo of the Milky Way. And that's also seen in lots of extragalactic sources. So Fermi has basically done everything perfect. They've measured Milky Way diffuse emission, they've measured Milky Way sources, they've measured extragalactic diffuse, and they've measured extragalactic sources. And what we want to do is replicate this success at higher energies and also eventually in neutrinos. So this is the quote low energy range, GV to TV. Now I'm going to focus my attention on TV to PV. So what do we have? In cosmic rays, we have abundant, wonderful precision measurements of all kinds of cosmic ray species and their fluxes as a function of energy. We know that these come from the Milky Way in this energy range. We have no information about sources in the Milky Way. We've got no information about what other galaxies are doing or their sources. We just know that there are accelerators all around us and we can't see them. But we know that they're very luminous. We know that they release very high energies. And we know that they produce not only protons and electrons, but positrons and antiprotons and nuclei and everything. This is the basic proof that there's a lot to be seen in gamma rays and neutrinos once we have the power. We know we have the accelerators and you can't accelerate without making a mess. So in gamma rays, we have had a great start. And here's a picture from Hawk. This is a picture of the Milky Way plane sort of zoomed in. And many sources are seen there. And also some diffuse emission. And we have a few extragalactic sources, but so far we don't have the extragalactic diffuse. So this is a wonderful start, and there's great things coming that are going to make this much better. So this is the second of the messengers. We know we have cosmic rays in the TeV PeV range. We know we have gamma rays. So what about neutrinos? Amazingly, in neutrinos, we have not detected robustly anything from the Milky Way. Prior to the start of IceCube, many of us were very hopeful that IceCube would see neutrinos from a variety of Milky Way sources, or perhaps the whole Milky Way diffuse plane. It hasn't happened at any high significance yet. IceCube has most definitely detected a strong extragalactic diffuse signal. That implies that the sources of these neutrinos are present in many galaxies, but not all, and including probably not in the Milky Way, at least not right now. And IceCube has a pretty good hint of neutrinos from one source, the so-called TXS source. But again, the diffuse emission seen here up to the PV range, even though this is spread across the sky and we haven't yet determined most of the sources, we know that the sources are there. It's just a matter of zooming in to find them. So how are we going to make progress in all of this? Next step that's happening is the LASSO cosmic ray and gamma ray detector is firing up in China. It's already producing results, and it's going to measure cosmic rays, but especially gamma rays. It's basically like a super Hawk, and it goes to higher energies. I'll show you results in a minute. And like Hawk, it does this great thing of basically scanning the entire visible sky above their location. This will be paired with CTA, which does not scan the full sky, but rather zooms in on one point at a time and can detect things with incredible sensitivity and angular resolution. So something like LASSO and something like CTA is a wonderful combination. The one on the left, it basically prospects the whole sky, and the one on the right can zoom in when you need it. We hope that this will also be accompanied by IceCube Gen 2, basically a 10 times upgrade of IceCube. And that would enable us to detect extragalactic and galactic neutrino sources robustly. I want to give one brief highlight here. I think Bei Zhou is on this call as well. Bei has led 3 papers recently on new kinds of signals for IceCube and IceCube Gen 2 that I think are very exciting, including W boson production and trident production, and including searching for those and other things through dimuon signals. So as IceCube eventually transitions to IceCube Gen 2, these kinds of more rare signals will start to become very significant. And like the flavor information, having more and more channels gives us more and more tools to unpack what we're seeing. Okay, so what LASSO is already doing is they've measured the crab up to energies of about 1 PeV. Now, when I was in grade school, I think I saw Francis Halson here. When I was in grade school, he invited Trevor Weeks to give a physics colloquium. And basically, Trevor was reporting the first discovery of gamma rays, I think it was from the crab, in the TeV range, or maybe it was Markarian something. But anyway, you know, when I was in grade school, the hot area was the TeV range, and now people are pushing the PeV range. And this is an incredible figure. I want you to just pause and really think about this figure. Over 4 orders of magnitude in energy. Look at that precision. If you were a collider experimentalist, you would be proud of this plot. It's not only the energy range, but like I said, the precision is just outstanding. And the fact that we're able to do this with an astrophysical source backs up my point that we're entering an era of precision astrophysics. LASSO is also finding a variety of other sources along the galactic plane, and this will be a really important partner to IceCube and Gen 2. What can you do with all of this? If you only care about particle physics, you can use it to understand what's going on with the neutrinos. You may have seen these flavor triangles like this, where we balance out the proportions of nu e, nu mu, and nu tau. And if there's a standard 3 flavor situation, those have to add up to 1. And on the left, we show basically what is possible in pure standard model. This sort of fish bone here, dog bone here, is this part of the space that can, pure standard model can only access this space. The next level of new physics models can access a somewhat larger space. And this will be really important as IceCube and eventually Gen 2 refines their measurements. And the beautiful thing about this is it's flux independent. It's just about measuring the flavors. You can also look for neutrinos interacting with the cosmic neutrino background. And this is so-called secret interactions. And we show here that IceCube Gen 2 would have incredible precision. This MI solution is proposed. It's a proposed alteration of cosmology to help explain the Hubble tension. And you see that Gen 2 could completely cover that space. Okay, moving on to the last section, which is the extreme energy frontier, the very highest energy. So this is, so EeV, maybe you're not familiar with this. EeV is 10 to the 18 electron volts, and ZeV is 10 to the 21. So we know that there are accelerators out there that go up to 10 to the 20 electron volts and beyond. How they do it, we don't know. We know that not only are the energies high, but they're so luminous that they can be seen across the universe. Well, we can't see the direction, but we can receive their fluxes. There could be evidence of supermassive particles that decay or something, but we don't know. We've looked, but there's a lot more to see. And these very high energies allow us to probe the cross-section at energies beyond the reach of the lab. So as these high energy protons cross the universe, they basically scatter with the cosmic microwave background and the infrared background and produce gamma rays and neutrinos. This is called the GZK neutrinos and gamma rays. And all of these highest energy protons, from the highest energies and the greatest distances, all of those protons die, and the neutrinos are their ghosts. And if the ultra high energy cosmic rays are protons, we get the most neutrinos. If ultra high energy cosmic rays are nuclei, we get fewer neutrinos. So measuring the neutrinos can be a really way to break an uncertainty in high energy cosmic rays about composition. Here's a picture of the Obj spectrum. Again, look at this precision. It's just outstanding. You can barely see the error bars on most of the plot. And even though we have measured this very well, we still don't understand all of the features or even the composition. There are lots of hints of anisotropies, but they come and go. I haven't bought into any of them yet. The key to cracking all of this is to go after the neutrinos. Because again, if these are protons, you get a high neutrino spectrum. If they're nuclei, you get a low neutrino spectrum. And here's an example of a way to do this. And here's some results, here's upper limits from IceCube and Anita and Auger on one model of the GZK neutrinos. And you can see the important thing is we're getting close. We have to not just get close, we have to actually detect this, and then we have to detect it with high statistics. So one way we're going to do that, I hope, will be IceCube Gen 2. IceCube Gen 2 has two important parts. It has a much bigger optical detector, like IceCube, but bigger and better. And it has a radio detector, which is incredibly huge and should be a very powerful way to probe these highest energy neutrinos. Many, many other proposed experiments, one of which I'd like to highlight is led by Stephen Prohira, who is a CCAP postdoctoral fellow here. And this is called the Radar Echo Telescope. Basically, ordinarily, when a neutrino interacts and makes a shower, we passively look for the radio emission that comes from it. What Stephen and collaborators want to do is image those showers by bouncing radar off of them and find them more actively. And this allows a greater aperture. So this might be possible to be scaled up to really huge sizes. On the MMA side, one of the very simple thing I want you to notice here, this is an E² phi plot. And what that means is the area under any one of these curves is proportional to the power density, basically the luminosity density of sources. And the incredible thing you see right away is that the total power in gamma rays is comparable to the total power in neutrinos, is comparable to the total power in the highest energy cosmic rays. And exactly how that works, we don't know, but this is clearly an important clue. This is a point that Francis Halzen's been making for a very long time. And Marcus Allers has really developed nicely. This is an important clue, and we have to measure all of these and then compare them precisely. How is this going to help us learn new physics? IceCube and others have already measured the neutrino-nucleon cross-section at very high energies. And in the GZK range, you could reach up to much higher energies, far beyond the reach of the laboratory. You can also look for more exotic models like Lorentz invariance violation. So to wrap up, the goals of particle physics, I think most of you are particle physicists, and why are you doing it is these things. Probe fundamental particles and forces, explain emergent phenomena, and search for new physics. And what we're doing in particle astrophysics to support this is this approach of trading off the particle physics and the astrophysics step by step. And how do you do this? You have to do it very carefully to not be hostage to the uncertainties on either side. And when it works really great. So the key messages of this, I think, are that multi-messenger astronomy is opening a really fantastic opportunities in both astronomy and physics. And this is a golden opportunity for us to learn about particles and using astrophysics, and to learn about astrophysics using our knowledge of particles. The overall picture is even bigger. This will help us just better understand how the whole universe works, connecting the most microscopic scales to the largest scales, the most macroscopic scales. And along the way, we will develop some of the most sensitive instruments humans have ever made. These can be used for a wide variety of other things. And I think it's just cool that we can better understand our place in the universe by better understanding both the smallest things and the largest things and how they connect. To close, I want to talk a little bit about how this all gets done. And Jordan is going to go into this in much more detail. I encourage you to look at, there's a giant report for the Astro 2020. Our chapter is something like 30 pages. It's much more readable. I encourage you to take a look. But last point I want to make is kind of the wait, but who? So the success in the field of physics, success for the field of physics, it depends on not just advancing technology, but advancing our human capital. And all of us have a responsibility and an opportunity to work to broaden participation in our field. This will make the field better. It'll bring in lots of new ideas. It'll make it more equitable, and it'll help lead to a more just and equitable society where the benefits of scientific research are shared more generally. I encourage you to look at things like the AIP Team Up Report and the APS ID, spelled it wrong, APS IDEA Project, things like that. Another important part of this is the importance of mentoring. For a long time in our field, it was sort of a survival of the fittest approach and very adversarial. I think it's much more beneficial to work on helping uplift our colleagues. And in that video, I talked quite a bit about that. And we all have a responsibility to share this excitement with the public. It's, people say, oh, we got to tell the taxpayers what we're doing. Yes, that's important. It is important. But we also have to inspire the next generation of scientists and help both the youngest and those who have not been reached by the benefits of science to understand that it's their universe too. Thanks.
Awesome, thank you. Are there any questions? You can raise your hand in Zoom, or you can enter any questions that you have anonymously in the Google form provided in the chat.
I don't think I can see any questions. You'll have to read them to me.
Yeah, looks like Frank has his hand up.
Yes, so thanks for this talk. You said that the composition of ultra-high energy cosmic rays is limited by theory, but that essentially can mean there are unanswered particle physics questions that we need to solve to surpass that limit by theory. So can you go a little bit deeper there?
Yeah, thanks. Let's see if I can go back a few pages. I don't think I have a picture of the composition, but here's the very precisely measured spectrum. There are also plots of X-max, which is basically the depth in the atmosphere at which particles interact, and then the variance in X-max. And the X-max distribution and the variance distribution are actually measured pretty precisely, so that the experimentalists are doing their job, but the theory is very uncertain. And basically, the theory uncertainties are larger than the experimental uncertainties. So how are we going to fix that? One thing that may help is measurements in very forward angles. There's a new set of proposals at CERN called what's it called, Forward Physics Facility, phaser and related things like that, that they want to measure basically all the particle physics that happens at extremely forward angles. I think that would be very helpful. But beyond that, we theorists just have a lot more work to do. Does that answer your question, Frank?
Partly, yes. Thanks. So,
thank you.
Awesome. Luis, I do see your hand, but in the interest of time, I'm going to ask you to come back to it at the end. And I'd like to introduce Jordan now. So our next speaker is Jordan Goodman. Jordan, if you'd like to start sharing your slides. Jordan is a distinguished university professor at the University of Maryland. He also received his PhD from the University of Maryland in 1978. He's been named a fellow of the American Association for the Advancement of Science and the American Physical Society. He studies particle astrophysics, especially cosmic radiation that probes the properties of elementary particles and their processes, as principal investigator for the Hawk experiment, and he is also on the advisory committee for SWGO. Jordan served on the steering committee for the Decadal Survey on Astrophysics and Astronomy in 2020. So Jordan.
Thanks, and thanks for the invitation. Actually, I'd kind of like to start just to echo what John said about, one of the things that the Astro 2020 panel did that's really relevant for everybody is we studied the state of the profession, and they can call that lively. And that is actually another interesting chapter and report to look at, which is they refer to as the SOPSI report. And it does talk about how it's important to increase participation and diversity across all people to really enhance the field. And I think astronomy has done a good job in some cases, and other cases not so good. And so they're at least looking at some of those issues of how to do that, and it's really important. And that's actually another good chapter to read. But as was mentioned, I was on the steering committee, and my role in the steering committee was I was also the liaison to the panel that John chaired in particle astrophysics and gravitation. So I just figured I'd give you a little teeny bit about our report and how it fits into what you guys are doing in Snowmass. So let me just click here, right, get the correct window. Okay, so our charge was to, did you see a change or no? Because did you see me change slides?
Yes.
Good. Okay, because my window here didn't. Anyway, okay. So the charge was to generate recommendations for the next decade of science in frontiers in astronomy and astrophysics. And the report was sponsored by NASA and NSF and DOE. And you know, it's interesting to understand how each of these agencies responds to Astro 2020. I kind of joke about it, but it's sort of true that NASA actually listens to the report and basically uses this as a roadmap and does what we say. NSF would like to listen to it, but it's not 100% sure how, because the way they're structured, they have panels and programs and things, and they don't really tell you what to do. They kind of listen to what you want to do, and then they respond. But they do occasionally create programs that are response to this kind of thing. And for example, Windows on the Universe came out of that. And you could argue that DOE doesn't honestly care. They're going to do what they want to do, but maybe not. So the whole point of this is that this part of the report is input to Snowmass and then to P5, which is what actually DOE listens to. And that's a really important thing to kind of get your head around, is that you are the interface to get this to DOE. So, you know, the Astro 2020, we've given talks about a lot of places, but it was it's like Snowmass, but for astronomy and astrophysics. We get community white papers and program white papers, and we have panels and put it all together. And we issued this report. It only took us 2 years. So it is very much like Snowmass. It seems to be interminable in its time, but hopefully it will come out. So one of the big themes that came out of this was, as John said, multi-messenger astronomy. And we have this kind of chart that talks about the various things and how they overlap. I saw there was a question about gravitational waves. Gravitational waves play a very important role in astronomy and in understanding a lot of the questions that we're looking at, including things like transients and dark matter and acceleration. And all of those things can be seen sort of in the overlap of this Venn diagram. But again, one of the main themes that came out of this was the science theme, new messengers, new physics, and to look at what is actually transforming the way we look at the universe. So we've made tremendous progress in CMB, and one of the recommendations of the Astro 2020 was to support strongly CMB stage 4, which is an interesting model in the following sense, that it's a CMB experiment, and this is my own interpretation, but 95% of what it's going to do might well be called astronomy. But the most important reason that physics funds it is the chance that it'll discover primordial gravitational waves, and that's actually a really important physics thing. So a lot of times things are leveraged between physics and astronomy in an interesting way. But we also talk about the importance of time domain surveys in optical and radio, and the fact that time domain is now extended to neutrinos and gamma rays. And the discovery, for example, of the LIGO black hole merger was one of the more important discoveries, or sorry, neutron star merger was one of the most important discoveries of the last couple decades. And it produced a tremendous amount of science. And of course, as John pointed out, the IceCube's detection of high energy neutrinos of astrophysical origin. So this is one of their slides. I would give you my summary of what how this related to particle astrophysics, which is that the main report, which, you know, you have to understand, there's an old saying that says money weighs less in space. And so when we kind of have to understand that when the Astro 2020 looked at things, they looked at large scale projects, and large scale in space is something that's more than several $billion. And large scale on the ground is something that's kind of $100 million up. So even though they're very different scale, that's what they kind of talked about. And the main report didn't get into smaller things than kind of $100 million projects. But the main things they did do is they endorsed IceCube Gen 2, but they didn't explicitly recommend it because they were charged to recommend to astronomy and not physics. And this is something that would come out of NSF physics. CMBS4, as I mentioned before, was recommended. They talked about tech development for the next generation of LIGO detectors. And they recommended something important, which does go down to the lower level, which is recommended enhanced funding for mid-scale experiments at the NSF. The PAG panel, the Particle Astrophysics panel, that John chaired, they recommended several experiments that are relevant. SWGO was recommended at a cost of about $20 million for the US participation in the CTA experiment, and continued support for the current generation of detectors that are operating and working in this field. So, and their two big ground things that they recommended in terms of stuff that physics should do is, again, technology development for LIGO and IceCube Gen 2. So they have a couple of timelines at which they kind of drew these pictures. Actually, I think I drew this one, but of when different experiments would come in the different fields. And the important thing here is to have capabilities that overlap one another temporally, as well as in sky coverage. And so they had the timelines for various things, and this will all depend on congressional funding and various other things. So this is the main Astro 2020 report. Okay, so the question is, what are some big questions for particle physics that are relevant to this stuff? Well, as John mentioned, extreme accelerators. I would point out that both dark matter and dark energy were both discovered in astronomy, okay? And yet they represent the vast majority of what our universe is made of. Neutrino mass and hierarchy are important questions. Again, extreme interactions. How do we, this was mentioned when we talked a few minutes ago about the Auger result. How do we understand extreme interactions of high energy particles way beyond the energies of accelerators? People are looking for axion-like particles in the cosmic rays, and Lorentz invariance violation and gamma ray bursts are some of the most energetic phenomena in the universe, and we're trying to understand that. And the evaporation of primordial black holes, if they exist, can give us an amazing clue, and I'll mention that a little bit later in my talk. And of course, we've seen already how the merging of black holes and neutron stars has produced tremendous understanding of how the universe and the elements were formed. And of course, there's this interesting question of the tension in the Hubble constant, which is derived, one from direct measurements of supernova and things like that, and the other from understanding CMB. And it potentially points to different understandings of fundamental physics. So let me give you a little bit of history from, here I'm an old guy. Yeah, she pointed out when she told me the day of my PhD, I did not get my PhD at 5 years old. So I've been around for a while. And so I want to give you just a little history of cosmic rays and their interaction and how important some of the stuff they've discovered is. So what I would call prehistory, which kind of dates before me, is, cosmic rays were originally where we discovered antiparticles and hyperons and pions and kaons, and the rising proton cross-section and that kind of stuff came out of early cosmic ray experiments. But in the pre-1990 period, one of the most interesting things was stuff that was not really intended to be so much cosmic rays, but had real impacts. So for example, the Ray Davis's experiment pictured on the right here of looking for neutrinos from the sun. And he detected them, but found that they were a third the value he expected, which was an interesting thing back in the day. And then the IMB experiment and Kamiokande were both experiments designed to look for proton decay. And instead, they didn't see proton decay, but they did see supernova 1987A, which had about 20 neutrinos and about 770 papers associated with those 20 neutrinos. But the other thing they both saw was something interesting, was looking at cosmic ray neutrinos, there seemed to be a deficit of muon neutrinos. And this fed back into our understanding of neutrino oscillations. But the other thing they did is they didn't see proton decay, which disappointing, but it actually gave us a real insight into particle physics by ruling out a whole class of models that predicted proton decay at a level that would have been detected by these experiments. And so these things were something that were direct particle physics things came out of these experiments. Now, the next generation of experiments that were built after this were an order of magnitude bigger, which is kind of the traditional way of doing things. You get scale up. And so Super Kamiokande, which was a water detector, we looked at solar neutrinos, atmospheric neutrinos designed to look for supernova. But when we wrote the proposal for Super K, we were explicitly told by our DOE program officer, don't mention neutrinos. And we were like, huh? He goes, nope, all we support is all high energy physics supports is proton decay. We won't learn anything from neutrinos, that's nuclear physics. Well, that wasn't exactly the case. Okay, so between Super K and SNO, which was built in Canada, okay, which was sensitive to all neutrino flavors, we showed that neutrinos oscillated, and that meant that they had mass. And this was the first real beyond the standard model physics confirmed, and it won a Nobel Prize in physics. So the part that we weren't supposed to look at was actually what produced the physics result. And that's kind of a theme. And so the Dune experiment, think of what we want, is an outgrowth of this work. And future detectors are going to, again, have sensitivities which are orders of magnitude more sensitive. So for example, they're loading Super K with gadolinium, and this will give it much more sensitivity to low energy neutrinos, including potentially, primordial neutrinos. And the plans are to build Hyper K, which is again a factor of 4 or 5 bigger than Super K. LIGO, we all know about. It's produced extraordinary results with the merging of black holes and the merging of binary neutron stars, but it actually, I don't know, astronomy, that's a good word down there. Okay, it actually ushered in the era of multi-messenger astronomy with the detection in August of 2017 of the coincidence of a short gamma ray burst and a merging binary neutron star. And this was just an extraordinary thing that confirmed a lot about astrophysics, but it also gave us a real understanding of some really important physics, including how the heavy elements were formed and lots of things like that. And as John mentioned, there has been multi-messenger observation by IceCube of TSX 0506, which is an active galaxy, which was IceCube had a neutrino, a high energy neutrino from there, simultaneous with a flaring AGN seen by both the Fermi satellite and by experiments on the ground. And so this was a really interesting thing. And then they went back and looked and found that they had an earlier burst that was consistent at least 3.5 sigma level from the same source. Weirdly enough, this source had a little prehistory that if you go back and look at the Egret experiment, which flew back in the 1990s, they had, because of a design issue, they had terrible sensitivity to very high energy events, but they had about 80 events above 10 GeV in their experiment. And when they went back and looked, of those events, all of them were individual sources that were right around 10 GeV, except for one source that had 2 gamma rays that were at about 45 GeV. And that source was this source, TSX 0506. So anyway, it's interesting. John sort of introduced Hawk a little bit. I'll just tell you a teeny bit about it as an example of one of these experiments that kind of gives you a sense of the kind of science we can do that's relevant to both particle physics and astrophysics. So here's a picture of Hawk. A lot of people show up, but I actually took this one. And to give you some scale, here's a guy who's like a 6'6" guy walking along next to it. These are giant water Cherenkov detectors. Each of them has 50,000 gallons of water in them. We're located in the high mountains of Mexico. We're at almost 14,000 feet. Here's the Pico de Orizaba, which is snow covered in the tropics. And it's an interesting place. And the idea is pretty simple. We just use timing of the shower to tell which direction it comes from. And we have a method of analyzing the shower that can tell you whether it was a gamma ray or a hadron by the shape of the shower on the ground. Here's a picture of slowed down of how a shower moves across the detector and gives us angular pointing to now about 1/10 of a degree or so in our highest events. So we're doing really well. We can point back into space, we can measure the energy, and we can measure whether it's a gamma ray. We can reject hadrons at the highest energies at a factor of at least 10 to the 4. So, and how it was built, it was a collaborative experiment built by NSF, who was the main sponsor, but it was critically important that DOE and Mexico, and then eventually Max Planck Institute in Heidelberg came in, but the main project was supported by NSF, DOE, and CONACYT in Mexico. And one of the critical things about this was it wasn't just the money that DOE gave us, and they put in about $4 million out of the 15. And this whole project costs like $15 million. So again, you talk about going from space, which is billions, to some of these big experiments, which are hundreds of millions. This experiment was $15 million. But the important thing is that it allowed Los Alamos to participate because they were a DOE lab. And it also said that Los Alamos, their LDRD funding actually contributed a lot to Hawk So the fact that DOE gave some money to the experiment, and I remember talking to them and they were like, oh, but they charged us high overhead rates. And I actually showed them an accounting that we got more back from Los Alamos than we put in to Los Alamos, which is pretty good. And this was a follow-on to a previous experiment, which was also supported, that developed the water Cherenkov technology, supported by DOE. And the reason it got supported is it was endorsed by what at the time was this particle astrophysics SAG group. There was a subpanel of HEPAP for the DOE that said support it, and then DOE supported it. So the important thing is these panels that you're part of with Snowmass and P5 have a real impact on what actually gets built, even if they're a minor part of the cost. So that's a message I want to give. And so what we've done with this experiment, again, a moderate price experiment, is we've surveyed the northern sky in gamma rays from approximately 1 to 200 TeV. We've discovered many new sources. We've discovered 40 or 50 branch sources no one's ever seen. Plus, we've seen 13 sources above 100 TeV. Some of them were later confirmed by LASO. LASO's seen some more. We've seen them now. It's a really interesting thing. But we've also discovered new source classes that nobody predicted. So, for example, this TeV halos, which is large extended objects. We've also seen that acceleration takes place in the jets of microquasars. So they don't just take place from them. Microquasar is kind of a laboratory AGN. You have a local black hole sitting around, it have a star feeding it, and it has these jets that come out. And we've seen particle with high energy acceleration above 25 or 30 TeV coming from the jets, because the electrons can't get from the particle all the way out there. So it's acceleration occurring out there. We've also seen the collective star forming regions produce high energy particles. We've set the best high mass dark matter limits using HAWK that exist. We've also set limits on Lorentz invariance violation. And I'll come back to primordial black holes because it's Christie's thesis, but we'll talk a little bit more about that. But example, we look at AGN, which are far away, and we don't see very many of them. But if you can see a really far away AGN, there's a limit on how far a photon can travel to get here through the extragalactic background light without pair producing. There's some evidence, not compelling yet, but that higher energy photons are getting through than you might expect. And one way to do that, and John would be a better person to describe this, is that if you go through an intermediate axion-like particle that doesn't have this, and then it decays back into photons. So by looking at some of these things, you have a way of looking for various particle physics things that are connected, and including Lorentz invariance violation. Let me just say a word about that. We've seen some of the highest energy photons anywhere. And the fact is that certain models say that certain really high energy photons under certain Lorentz violating scenarios could not propagate. And the fact that they do sets some limits on Lorentz invariance violation. Okay, so here's a map of the galaxy as we've seen from HAWK. Here, this is the southern sky, which we don't see because the Earth and atmosphere is in the way. This is a very northern sky, but here's the galactic plane, and you see lots and lots of sources. And John showed one of these pictures earlier. I'll show one of our more recent past 5 pictures, which you can just see we've got tons of sources, and each of these little green lines starts at 15 sigma. So you're talking about things that are 50 sigma, 100 sigma, of detection. And we're trying to, at this stage, we're in a very data-rich environment, trying to separate these things and understand the various acceleration mechanisms and processes that accelerate high-energy particles that give us high-energy photons. Okay, just to go back to the primordial black holes as an example of something that would impact particle physics. So if you created a small black hole at the early part of the universe, mass of say 10 to the 15th grams, kind of not that big, but still, it would, black holes slowly evaporate. And as it evaporates, it loses mass and its temperature goes up like the mass, like 1 over the mass. And as at the end of its lifetime, it's really hot. And a PBH would radiate all the fundamental particles whose wavelengths are smaller than, whose wavelengths are larger than the size of the black hole. So as the black hole gets smaller and smaller, at the end of its lifetime, it would radiate particles of extreme energies. And the gamma ray flux, if you could detect one of these things, would look like a gamma ray burst, but the spectrum would get harder and harder, and then it would just go pop and disappear. And as a black hole evaporates, all the fundamental particles will be emitted. And by counting this emission, you would count the number of degrees of freedom. So discovering one of these things would give us an amount of particle physics that you couldn't get by building the next generation detectors an order of magnitude bigger. So John did a great job mentioning IceCube Gen 2. I'll just say that it's a US effort that's being led with but requiring European support. It's a really exciting project that will have a tremendous physics reach in a number of ways. A picture of it. The idea is that you get a factor of 10, but you only spend about a factor of 2 in cost by you double the cost of the original thing, but it's only another one more IceCube cost-wise. But by having to get the highest energies, you spread the strings out to get really large lever arm. CTA, as John mentioned, is another thing which is being built by the Europeans. It's actually being built. It was one of the top recommendations from Astro 2010 for the US to participate. And I say this because it's true. P5 basically put a poison pill in it. They said, oh yeah, we should do this as long as astronomy pays for half of it. And astronomy, the one thing I learned by being on Astro 2020 is that the astronomy budget is not small, but most of it goes into facilities. And individual astronomers are in much worse shape than individual physicists are in terms of getting grants. And the amount of grant money they have and the amount of abilities for them to support projects that don't come down as a big effort from the top, like an MREFC or an observatory, is very minimal. So it really killed off. The US was one of the people who were pushing this idea for CTA originally, but we have yet to be given support to participate in it. So this is something. Now, SWGO is the next generation of what the people mostly working on HAWK would want to do. It's a complementary array to HAWK and LASSO and CTA. It would be built in the south where there is no wide field observatory, and it would allow us to look at places like the Galactic Center and this much better. It would be at a higher altitude with a lower threshold, a much larger area, higher density, and it would be ideal from transients, and it would be a joint US, European, and South American projects. So these are some of the things on the horizon here. I would point out to you that the DOE has played an important role in many of the important astrophysics experiments. So, and this is not meant to be inclusive because I just pulled it out of my head when I was writing this down. So I know that SLAC has been involved in the Fermi Gamma Ray Space Telescope. They built the silicon, the dark energy camera that they're building now. They've been involved in the Vera Rubin Observatory, the LSST, which is just starting to take data. Fermilab was a major player in Auger, the Sloan Digital Sky Survey, and the Dark Energy Survey. Los Alamos was critical in building Milagro, HAWK, and they're playing a role in SWGO. Argonne has been part of Veritas, the South Pole Telescope, that's a CMB measurement, and CMBS4. And LBNL has been part of IceCube, DESI, and that's the Dark Energy Spectroscopic Instrument, and CMBS4. And so these are all critical things, and they're supported because Snowmass and then P5 says, yeah, do it. So I just want to give you a little bit of prehistory here, which is that the US innovated a lot of the stuff that's going on. As John pointed out, Trevor Weeks was the first person at the Whipple Observatory in Tucson to see any gamma ray source with a Cherenkov light telescope. I was actually at the meeting in 1988 when they announced the discovery of the crab, and that collaboration, the Whipple collaboration, proposed building this thing called Veritas, which is up and operating, but it's actually some of the important stuff was scooped by the Hess experiment in Namibia, because although Veritas proposed and designed the experiment, by the time the US got around to funding anything, the Europeans had already built something. And so it's really critical that we advance the things that we've designed and that we support them. When it came to neutrinos and proton decay, as I mentioned, the IMB experiment was a US DOE project. The Japanese built Kamiokande to do the same thing. We started stuff in the deep ice with the Amanda experiment, and then Ice Cube at the South Pole. And of course, Ice Cube is doing great, but there's now other experiments. People who are doing the same experiments. There's KM3net, which is being built in Europe, and Lake Baikal experiment, which is being built in Russia. And there's this thing now called P1, which is in Canada, wants to build a large water Cherenkov detector off the coast of Vancouver. In wide field gamma rays astronomy, Milagro and then Hawk was the first experiment to show how well this worked. And the Chinese built LASSO. And what the Chinese did was we spent about $15 million on Hawk. They spent about $250 million on LASSO. And we kind of built Hawk with local workers from the little town of Otacintla. They had a construction company that built the Three Rivers Gorge Dam, which was the largest construction project in the history of the world. And they built their experiment, but it's because resources were available. So let me just end here by telling you the importance of Snowmass. So I'm not saying you should write down that this is the experiment that you should do, because all proposals have to compete on their scientific merit. But with DOE, they don't have a chance. They don't get in the door unless they're endorsed by Snowmass and P5, because it's very easy for them to say, well, we didn't see that in the proposal, we don't do that. Because DOE is very mission directed, and the mission comes starting with Snowmass and winds up in P5. And DOE and DOE labs provided a lot of leverage with other agencies. And I think it's important to even look at it from the lab scientist point of view, which is that the lab scientists, you have opportunities for them to work on experiments that first off give data in a finite amount of time, and second off where they can get their hands on and use developments they've built in their laboratories that can be used for astrophysics. So my final message is here, you need to tell the DOE the importance of astrophysics to particle physics. And that's what I think my message is. So let me stop there, and I will be happy to take questions.
Thanks, Jordan. That was a great talk. So if anyone has any questions, feel free to raise your hand. I think we also still have the Google form in the chat somewhere if you'd like to submit anonymously.
Figure out where my Zoom window is here. I will get to it and I can see that too, hopefully. Okay. Yeah, I see it moved over to my third monitor. So I can't see if anybody's got any hands up yet, but I will in a second. Okay.
So we did, while people are thinking about questions for Jordan, we did have some questions that were recorded in the chat previously. So what is added by gravitational waves to our understanding of astroparticle physics? And that was asked by Rita Simbruna.
That's a great question. So for example, in the binary neutron star merger event from several years ago, the gravitational waves help us identify what's happening, help us figure out that it was a binary neutron star merger. And that's a key detail that happens on very small distance scales that can't be revealed any other way. And knowing that what's powering the overall event helps us understand the overall astrophysics. That's one answer. Does that answer your question?
Yeah, it's starting to address it. The thing that I'm also wondering about is there are very few of these mergers who have electromagnetic counterparts. So what do you need to get insights into you were talking a lot about combining all messengers, and electromagnetic is something that may not be present for these mergers.
Yeah, so great question. The upgrade path for LIGO is, the planned upgrade path for LIGO is going to bring a lot more sources. The proposed upgrade path for LIGO would bring incredibly more. Jordan, maybe you can comment a little bit more on this.
Yeah, I think that, it's important to recognize that while, a lot of times it's important to measure lots of things, lots of times, a single solitary event like supernova 1987A, like the binary neutron star merger, gives us tremendous insight if it's well measured by a number of sources. So yeah, it would be great to have a lot of these. And part of the reach that LIGO will get will be further than the electromagnetic spectrum will get us. But by having wide field observatories, they can look at over a large energy range. For the events that we do see, we have a chance to really make important fundamental measurements, which was the case obviously with, with Fermi being, seeing the gamma ray burst, which it came that close to not seeing as they went into the South Atlantic anomaly, right? Because the lat was even off during that, but they were just, So, but having observatories that can look at this thing, there are proposals to build the next generation observatories that are in the MEV range, like the MIGO experiment, or MIGO X, or something that would have a longer path length to look for some of these multi-messenger events. And of course, neutrinos can go as far as they can go. So, the idea being that you could, one of the things you really hope to see is to look for some of the stuff and see it in these multi-messenger things. And sometimes limits are important too. The fact that you don't see it tells you something important.
Thank you.
Thank you.
So I'm still looking for hands, and we have another question in the forum asking if you can explain a little bit about why it's difficult to localize gravitational waves.
Jordan, you wanted to start on that one?
Yeah, it's actually not, especially with it's not, okay. So the first thing is the way you gravitational wave, any individual detector sees it basically just has the two arms, and it gets two signals from the two arms. The strength of them tells you what direction, and then you have two gravitational wave detectors, and then you can get an arc that tells you where it is. And then when you have the third, which you now have with Virgo, you get a point all of a sudden. So it's like the three things to find point. But again, there's some fuzziness in that. I mean, the binary neutron star merger was not seen by Virgo, which actually told them where it was, because they would have seen it had it been further over. So they were able to put it in a region. And then of course the optical comes in and was able to pinpoint it precisely. But as we're now in the stage where we're getting more gravitational wave detectors coming online, Kanga and others, and the one in India, and the whole point is that when you have a number of them, the localization gets better and better and better. And then once you can see it with an optical telescope, you can get it down to micro arc seconds or something, so you know exactly where it is.
Yeah, so to build on that point, Earth is about 40 milliseconds across. And so suppose you measure a time difference between two gravitational wave detectors of, let's say, 4 milliseconds, then basically you've picked out a band that's has a width of about roughly 0.1 in cosine theta. And that gives an arc on the sky, like Jordan said. So like, let's see, if I have two detectors like this, maybe you can see this. If I get the signal here first, and then I get the signal here second, then that tells me that the source was somewhere in front of me. And then in fact, a ring on the sky is what's allowed. And as Jordan remarked, with multiple rings, you can start to get them to cross. But fundamentally, LIGO, each individual detector has not too much localization uncertainty. It's just a vibration detector almost. And it's the comparing the different detectors that gives the best localization. That's why it's hard. Does that answer your question? I'm not sure who asked it.
I think that answers the question. So we have another question on the forum, and it's asking about the prospect for LISA becoming a reality.
I can talk about that. LISA,
we hope so.
Yeah, I mean, LISA's chunking along in Europe. I mean, it's on the European thing. It's got a scheduled launch date that's kind of around 2033, 34. They may even push it up depending on what's going on. And Astro 2020. So originally LISA, another experiment. LISA started off as a U.S. experiment concept out of Goddard here, okay, in part, and the people who worked on it were here, and then it kind of wound up as becoming a joint U.S. European mission, and they were going to do it 50-50. And then people discovered that 50-50 is probably the worst way to do a mission because nobody's in charge. So the Europeans said, okay, we're going to be in charge, and we're going to contribute a larger sum of money, and the US is contributing components of it, lasers, the soft ride system, and data analysis facilities to do this thing. And we are contributing our share of LISA, and the Europeans are building it. And one of the interesting things is they did this this Pathfinder mission to show that the system could work, and it worked much better than they even anticipated. And so everybody's excited about the prospect that LISA will actually happen. It's, you know, if you think Webb was complicated, LISA's 3 times, you know, more so, you know, but it's still interesting.
Awesome, thanks. So in your opinion, what is the most important energy range for new instruments in the coming decade, given the science goals?
Well, obviously the ones we work on. No, I'm just kidding. Anyway, I mean, I think the message from this talk is that all the energy ranges contribute significantly. In neutrinos, going higher is important. Going lower is potentially a little fuzzier, but you can go, if you go to lower, you can actually measure hierarchy if you put a little more instrumentation into IceCube Gen 2 and some of those new upgrades they're talking about. You could do that almost, you know, probably timely wise with Dune. So there's lots of things, depending on what your goal is, what energy range you think is important. If you want to understand where the highest sources in the universe come from, you want to go to the highest energies, and developing new radio technology and doing that kind of thing is really important. But also having comparable full sky coverage. So one of the things that was discussed, but it's an important issue, is that a lot of this multi-messenger stuff is dependent upon the NASA satellites, which, like me and John, are getting older. You know, it's, you know, you don't know when things start to fall apart. And so right now, we, you know, Fermi is beyond its projected lifetime. Swift is well beyond its projected lifetime. You know, Fermi's kind of got a wing that's a little bit balky, and, you know, things are, you know, but hopefully, so there's important, if we want to do this, to maintain those facilities as well, and particularly the ones from space. It's crucial that we have a next generation plan for putting things into space.
I want to add a little bit to Jordan's remark. So, you know, in laboratory particle physics, especially on the collider side, there's often a focus on reaching the single highest energy. And that's been the, you know, the march over decades. And I think one of the key messages of Astro 2020, Jordan highlighted this too, is that instead of one detector in one energy range, we put all of our energy and all of our money into one detector. I think the overall message of Astro 2020 is we need to look at a variety of detectors with a variety of capabilities, all operating at the same time. It's basically Astro 2020 says multi-messenger astronomy is astronomy. And I would rather have, you know, 5 different experiments that are more medium-sized than one experiment that's giant-sized.
Awesome. So how do you detect a primordial black hole burst, and how do you tell for sure that it is a primordial black hole burst?
Okay, actually, in theory, it's a very easy, it looks like a gamma ray burst, which you'd have to see. So all of a sudden you'd see, you'd start to see a spot in the sky, some random spot. It wouldn't be a star, it wouldn't be a, you know, thing that would just start emitting gamma rays. And it would, the flux would just start rising very quickly. And so you'd see this sudden burst, which we trigger on, we look for them now for gamma ray bursts, but the idea is you'd have this sudden enhancement of the flux. And the way you would distinguish a primordial black hole from a gamma ray burst is the spectrum would get harder and harder, and there would be these jumps where you get to a new threshold degree of freedom, which would give you more particles emitted, and then all of a sudden it would just go and be gone. And the gamma ray bursts tend to linger. So that's how you distinguish the two. And of course, the better you measure it, the better you know it will be there. And we're looking at these things that for anybody likely to detect them, they'd have to be relatively nearby for us to see them, you know, kind of in the parsec scale things, you know, not too far. But the point is, you don't know, and you wouldn't know where to look. So you need a wide field detector to look for it, because there's no way you'll have any idea where it would be. And maybe, you know, some of these things, you know, you might start seeing some emission in the, you know, MEV, GeV for a few hours before the burst, but all the action happens in the last few seconds. You know, it's really one of those things that just goes and gone.
Fascinating.
Yeah.
So
really pretty cool.
is there any potential cooperation that will happen between the US and China on astroparticle physics in the near future?
Challenging to say.
It's a good question. I mean, look, I mean, you know, the answer is possibly. I mean, actually, the Chinese have expressed interest in SWGO. Okay, they've maybe even in a particular way of expanding the array to the outer, you know, going really big. You know, we're talking about a kilometer square, which is kind of what they are. And they're saying, wow, why don't we build 4 kilometers square? And, you know, so the Chinese have something which they could add, which is money, which is important. But they also have some expertise. And I think, you know, we would be happy. I think there's none, even now we're working on being able to do some joint analysis between HAWK and LASSO, and in particular the fact that we cover different hemispheres. So if there's transient events or flaring AGN, we're working together right now to produce code that will allow us to plot the thing from as it moves from one field of view to the next over the course of the day. And so the answer is cooperation is certainly something we'd be willing to do.
There's a bunch of really fantastic scientific projects in China. I mentioned LASSO is really a superstar. I think all of us scientists believe that international cooperation on research is not only leads to the best science, it also leads to better understanding of peoples and nations, and that this is a really important and overall good humanistic endeavor for that reason alone.
I would add,
you know, our government is the one that makes the decisions, and their government. Other governments make the decisions, not us.
right. When it comes to LASSO, though, a lot of their stuff looks a lot like HAWK did because we gave them our simulation so they could design it. So they actually used the HAWK simulations to do the design of LASSO. And we spent a lot of time talking with them about what they need to do for water quality and other various things. And so we were cooperative to help them create the project. And so, you know, and it's, you know, if it looks a lot like, you know, some designs from HAWK in places, it's not because they stole it, it's because we gave it to them. So intentionally.
Awesome. So I'm still reading from the form if anyone wants to submit additional questions there or raise their hand. What more can be gained from better resolution of the CMB measurements?
Well, I don't know. I mean, John probably better, but I would think that the first thing you want to do is get, the main goal is primordial gravitation, you know, is primordial gravitational waves. So it really is not so much precision measurement there, but you're looking for these B-mode oscillations and being able to make more precise B-mode oscillations, you know, which are kind of the rotating, you know, has a curl to it, the gravitational wave. And, you know, and now I've told you everything I know about that.
Awesome.
I don't have a lot more to add. I'm primarily a particle astrophysicist.
Yeah. So we have one more question. How can early career scientists support the message of particle astrophysics, especially in the context of Snowmass?
Well, I mean, you know, the first thing is, besides the fact that you're here today, I'm really impressed to see that this whole group and what you've organized over months and getting to know each other and is very important. Writing, you know, the Snowmass white papers and, you know, giving talks, advocating for your science. That's basically the same message that Jordan said is, you know, find ways to advocate for the science that you think is most successful. And, you know, you'll be the ones leading the field over decades, and together you have a stronger voice.
I would also add that, you know, it's important to recognize that the potential career opportunities that these things give. as experiments, like the CERN Collider, most people these days can't get their hands on it. So they don't get they don't get skills touching experiments and doing things. And that's a real detraction, especially for the young people, who don't get a chance to actually, in our field, typically people work on everything from the hardware to the analysis to the thing that everybody wants these days, which is dealing with mega data sets. Hawk data set right now is 7 petabytes, I think, or 6 petabytes. And, that's something that some of our postdocs of careers have gone into working on that. And it's the kind of thing that, my colleague Andy always points out that Vera Rubin has like this entire budget of, they have a huge data set, but they have like the amount of money they're spending is their data set's like maybe a factor of 3 or 4 or 5 bigger than Hawk's, but the amount of money they're spending is about a factor of 100 more than Hawk on the data stuff, because we tend to do it ourselves. And so if you're advocating for the potential career path that takes you through here, I've sort of started in cosmic rays, but the rest of my group on IceCube here started in accelerator physics. They're both, and people are came out of CDF and other experiments, and they've worked on these things. And I think the young people advocating for the opportunity to work on experiments where they can have a more complete role in the experiment is something to make an important point to. And I think these experiments are still that kind of experiment where people get to go and work on the hardware and deal with the data at a fundamental level and actually, touch stuff, which for experimentalists is important.
Awesome. That's a great perspective. So I want to thank both of our speakers, Jordan Goodman and John Beacom, for joining us today and sharing their wonderful talks. I do want to close today with another advertisement for the All Cosmic Frontier meeting, part 2, happening on Tuesday, the 5th of April. If you need the contact or you need the registration link for that, you can be in touch. If you have any additional questions, feel free to email them. And thanks again to John and Jordan.
Thank you.